Hey everybody, welcome to Office Hours. We'll get started here. If you have any questions, let us know. We'll get started on some questions. Just my volume's around out here. There we go. There we go. So if you are here, if you are live watching Office Hours, I might start out with some 201. They have an assignment coming up tomorrow night, and that'll be a good time to review that assignment. Let's go ahead and take a look right here. So many messages. Okay, the assignment tomorrow night. Homework, confidence intervals for proportions. Let's go take a look. And let's do the homework. Okay, so we're getting the homework up and going right now. Who all is here? If you are here, let us know. We'll hop in here. Let's do some homework. Let's do it. Okay, so we've got the homework up and going right now. We're going to take a look at some of the questions on it. So this one right here is having us interpret a confidence interval. So with this one, it's important to know the interpretation. I go over this in the video on how to interpret confidence intervals. We need to say, I am blank % confident that the true blank is, well, blank to blank. Okay, so this is the key part right here, is that when we interpret the interval, we need to make sure that we do the four parts of it. I am blank % confident that the true blank is contained in the interval blank to blank. So let's take a look at our interval right here and see if we can interpret it. A catalog sales company promises to deliver orders placed online within 3 days. Follow-up calls from a few randomly selected customers. Random sample right there. Good. Condition number 1 shows that 95% confidence interval for the proportion of all orders that arrive on time is 88 plus or minus 2%. And so what we're saying right here is, think about it, the confidence level is 95%. So let's go to our confidence level. I am 95% confident. And what are we trying to estimate? They're trying to figure out the true proportion of all orders that arrive on time as classified within 3 days of the order. So we can literally take this and we can say the true proportion of all orders that arrive on time. If you notice, this is what we'd say is the population parameter right here. This is the parameter of interest. Those are synonymous words right there. Population parameter, parameter of interest. Those all mean the same thing. So the true proportion of orders that arrive on time is the second part. Here's I am 95% confident. And then it was 88% plus or minus 3%. So we can go here and go 85%. And we can do it as a decimal. We could go 0.88, or excuse me, 85 to 0.91. And so these are the last two right here. And you can do it as a decimal or as a percentage. But I am 95% confident the true proportion of all orders that arrive on time is contained in the interval 0.85 to 0.91. Now, it's very important to note, we'll go back here to our original interpretation before we do any changes to it. Here it is, and here's the correct one, or at least the filled in one. It's to note kind of the importance of context right here, that I am 95% confident is our confidence level. We need to delete this so it's a blank again. And then that the true proportion, so we're talking about the proportion this time, we won't always be talking about the proportion, is contained in the interval blank to blank. So you really have four parts to this. Your confidence level, so here's your confidence level. You have what you're talking about, which is the context of the problem. And then you have the interval you're giving it in. You're saying, I am 95% confident the true proportion of all orders that arrive on time is contained in the interval blank to blank. And then you give the interval. So practicing this right here, understanding this interpretation. Hey, Charlie, do you want to do some visualization help? Which one? The video's posted, or do you want to go over it? What do you want to go over, Charlie? I was doing the homework again right here. Your call. You're here. You get to call it. So select the statement that best describes the confidence. I am. One can be 95% confident. The true proportion of orders that arrive on time is contained in the interval. Oh, and I did it wrong. I put the wrong numbers. I did 3%. It should have been plus or minus 2%. Oh, no, jump gives the interval. Jump definitely gives the interval. Jump definitely gives the interval. Do I still have it up? I don't have it up. Jump definitely gives the interval. You don't have to, yeah, we don't figure stuff out by hand. At least when we're doing stats. If we're doing like calculations. So the formula video was just, oh yeah, just explaining it. Oh yeah, so you did watch the video. Yeah. So yeah, so in the video, great job, Charlie. Excellent work. Yeah, I was just explaining it. I was just walking through. That was just extra. So basically, people should always still read the assignment and then understand the parts of it. But jump will give you the interval. So I didn't do born in TN, but we can do it. So when you make your interval, you go here. You can don't make it 95, but you can get your intervals pretty quickly in jump. And so it actually gives you the 95% confidence interval. So I would say here, I am 95% confident the true proportion of Stat 201 students born in Tennessee is contained in the interval blank to blank. So if you notice, this is really good practice on the interpretation. You need to grab the whole thing right here. This is just an example right now. But you need this whole thing. I'm too afraid to not take the whole thing and then someone doesn't do it. So with this, we need to now use our interpretation. We'll do a copy of this right now so we can make it go back. I am 95% confident. That's the first part. And then true. Oh, I already wrote true. Proportion of Stat 201 students born in Tennessee is contained in the interval, and then 0.57835, 0.622296. You can put all the decimals if you want. Because we're done with content. Yeah, I jumped in and thought there would be people asking questions, so I don't have all of mine written down. But I need help reviewing the definitions from the chapters like sample frame. Oh yeah, we could do that. Let's do some review. Yeah, no, definitely. That's a good question. Review questions right there. And let's do it. So if you notice right here, did I destroy my copy paste? No, I didn't. So practicing this interpretation is key right here. I am blank % confident that the true blank is contained in the interval blank to blank. But you have to talk about the parameter of interest right here. This part right here is always a parameter of interest, which is a longer thing. So this is parameter of interest. So that's always your parameter of interest right here. I thought it would go to the next line. Oh, because it's got the spaces. Because now it will go to the next line. So that's the parameter of interest. Oh my gosh. That's your confidence level. So this is C level. And down here is just your upper and lower bound. So this is your upper and lower bound. So hopefully this makes a little more sense of it too, seeing it maybe this way to be like, okay, here's my upper and lower bound of my confidence roll, and there's my confidence level. So take a look at this right here. I am blank % confident that the true blank, and you have to talk about the parameter of interest, is contained in the interval blank to blank. So that's kind of the key right there. Ignore all. I am blank % confident that the true blank is contained in the interval blank to blank. Yep, we're done with content. So let's do this. Let's talk about, this is chapter 10 review. So chapter 10 is on sampling. So let's bring this up right here. It's off the screen. So let's bring up some concepts. So concept review from chapter 10. Concept review from chapter 10 is going to be, we have sample, let's go top down. Population, sample frame, sample. So when you do these right here, they can get smaller each time. They generally do. So you need to be able to define each of these and think about what they mean and then give an example. That's the one you really know it. So a population is going to be every person or thing we want to understand. Every person or thing we want to understand. Yeah, Dan, I can feel free to ask some questions on that. We can go back to that. I'm going to review these concepts right here. And then feel free, we'll go back to chapter, which one? Feel free to ask any question you want on any of them. It's your guys' call. You're here. So feel free to ask. Population, every person or thing we want to understand. Sample frame, every person or thing we have access to. Sample, every person or thing we sample. So when you think about this, the population is always going to be the biggest. The other ones can be as big if we do a census, but the population might be all Stat 201 students, which is what we're doing in our project. And your sample frame is pretty much going to be the ones that we have that gave responses. And then your sample is going to be the random sample you take. So when you think about it, you have access to a lot of the students because we got responses from a lot of 201 students, but you want to talk about all 201 students. You only have access to the ones to sample from the 1,000 or so that I think we give you. And then the sample is going to be the 100 so on amount that you take in your sample. So it generally gets smaller. You might say, well, generally, if you have a census, a census collects data on the whole population. So you'd have to want to understand. So the sample is the number of responses almost. Yeah, exactly. This is number of responses. If you have so many responses, that's your sample. Yep. If people, and then because that's the responses right there. So I use the same word. Every person or thing that we have data on. So that's, I shouldn't use the word in the definition. Like the sample is what we sample. It makes sense to me when I think about it. It's like, well, you take a sample and the sample is the sample, but the sample is what we have data on. So I shouldn't, sorry about that. I just realized I put the word in the definition. But every person or thing we have data on that give responses. So when we get responses, they become the sample. Does that make sense right there? Dan, good catch. So every person or thing that gives us responses that we collect data on would be our sample. And if we have a census, we have data on the whole population. So that we would have we would take you wouldn't really call it a sample then, you'd call it a census because we did a census of the whole population. And Dan, which one were you working on? Chapter 13. Let me know. Got a lot of time here today. Oh, and then what other were you wondering about the other? So this right here can catch people off guard. Sample frame, sample proportion, parameter, just lots of definitions. So when it comes to sample proportion, so there's other things. So the sample proportion is a statistic. So we have here the categories of statistics and parameters. So let's insert a table real quick right here. And we have the category of statistics and parameters. So there's a difference between a statistic and a parameter. So a statistic comes from a sample. So we have here a statistic. We have here parameter. So a statistic would be something like the sample proportion, like you said there. So sample proportion. So everything right here will always be called sample. So it'll be sample no matter what we say. And this is called population or true. So you can call it population, proportion, things like that. So when we go right here, and let's do this, let's add in one more column. Insert column to the left. Okay. So we need to make this bigger now. Bring it over here. And we'll make this smaller. Okay. And we'll do this. No. There we go. And here we go. There we go. Chapter 13. And what does that one say? The quiz will mix stuff up on me. Quiz chapter 13, question number 3. If you tell me the start of it. Thank you so much, Dan. Let's say right here, variable. So this is just the variable we're trying to collect. So if we have here the proportion, then this will be, and I'll write these in right here. If we're doing the proportion, this will be P hat, and this will be P. If we're doing the mean, then the mean will be Y bar, or the true mean, which is population mean, will be mu. If you're doing standard deviation, then the standard deviation as an estimate, which is the sample, will be S. And as a parameter, it'll be sigma. And I think the only one, well, then you have sample size. Well, you have size. Size as a sample will be N right here, little n, and as a population will be big N. It's going to confuse people. Because we talk about normally distributed, that doesn't mean sample size right there with a mean and standard deviation. But so I don't want to, maybe I won't talk about it. Things overlap sometimes, so sorry about that. I think these are the major ones you need to know. Don't worry about sizes. Here we'll just write N right there for sample size, lowercase n. There we go. What about big N is 6 of the parameter. So there is population size. 24%, you got it. We'll do that one next. So population size we so rarely talk about. It's just that if you were to say, the population size of the U.S. is something like 37 million or 370 million, and we take a sample of 2.5 million. So that'd be the notation on that. So this is more of a notation thing right here. where you'd say the population of the US is 370 million. We take a sample of 2.5 million. So that's just saying how many total there are, but be very careful because I don't want to confuse the topic. So I'm almost not putting it in this chart because we so rarely talk about it. I just don't want people to be confused when we do something like this because that's not population right there. What does this say? This says the distribution is what? This would say that the distribution is what? How does that read? It's just a repeat of a same notation thing, but it's using it. It's not population size right here. It's saying the distribution is normally distributed with a mean of 0 and standard deviation 1. Exactly, because this position right here maps to the mean, and this maps to the standard deviation when we do normally distributed with a mean and standard deviation. So it's just that two people wanted to use large N right there for something. So I don't want to put it in this table and then people think, oh, the population size. Like, no, that's just same notation being used on two different ideas. We don't use population size so often, so I'm not so worried about that. We use sample size way more often. So every time you see one of these, you can say sample standard deviation, sample mean, sample proportion, sample this, but it technically is, it's technically, in this table right here, big N would go right here because that would be population size. And then it's different if you do normally distribute with a mean. Here we'll do this. We'll draw this right here. And then we'll put a not, like these are not the same thing. It's two different concepts. It's just notation overlap when people say, I want to use it for this. And someone says, I'm going to use it for this. It's like, well, we're two people using the same thing. It's just two people. Same thing. Same notation, but different meanings. So sorry for any confusion that might cause. But yeah. Awesome. So there's a good notation review. So when you say things like the sample proportion, so sample proportion, and then parameter would never go with sample because parameter always goes. So this is where we talk about SSPP, because whenever you say a sample, you're talking about a statistic. Whenever you say a parameter, you're talking about for the proportion. Does that make sense right there, Charlie? That whenever you're talking about a sample, you'll get a statistic from the sample. Whenever you talk about the population, you're trying to estimate the parameter, which is the truth. This is the truth. It's like, what is the true proportion of UT students who are born in Tennessee? What do we see in a sample for the proportion of students born in Tennessee? What is the true GPA of UT students, like for all students? What is the sample mean that we see for students from a sample? Like if we take a sample of 100 students, what was the mean GPA for that sample? What is the variation within GPAs for all students? See how this is all because it's population. What variation do we see in a sample of students? This would be how big is the population of students? How large of a sample did we take for students? So everything here relates to a sample, and everything here relates to every single observation. Is a sample proportion used to make an inference? Exactly. That's 100% true, Charlie. Because imagine if you wanted to see, do UT students think we will win? Are we playing Kentucky this week? Who are we playing? Georgia? Who are we playing this week? I'm so bad. All I know is Dig Dug. Who are we playing this week? If you want Alabama. So if you wanted to see if UT students think we will beat Alabama, could you talk to 100 students? And see, this is really good. What we're gonna do, watch this. we're gonna talk to 2,400 UT students, which is, we're gonna say less than 10% of all UT students, because I think we have more than 24,000 students, right? We'll say we do. We're gonna talk to 2,400 UT students, and 24% of them think we're gonna lose to Alabama. So here we go. You ready? You ready, Dan? So we want to figure out the true proportion of UT students who think we will lose. We talk to 2,400 UT students, and 24% of them think we will lose to Alabama. Hey, Gigi. Can you do? Yeah, we'll do it next. You got it. Alabama. Estimate or construct. What kind of confidence interval should we construct, Dan? What kind of confidence? 95, 98, 99, 90. This is going to be a weird one, like 92. Construct I'll let Dan tell us, blank percent confidence interval to estimate the true proportion of UT students. 97? They chose 97? I don't know that one off the top of my head. Is that the one in your question? Wow, that's a weird one. It's going to be like 2.19 or something. Because 2.326, no, it's gonna be like 2.23 or something. Instruct a 97% confidence interval estimate the true proportion of UT students who think we will lose to Alabama. Okay. So the first condition right here is that we randomly select these students. So we passed that condition. We passed the first condition, which is random. We got to press that button. We got to make it happen. So we have random. We randomly selected the students because we don't want to go to the I Love Alabama group. And then they're like, oh, of course UT's going to win. Was there a certain percent I had to pick? I was figuring we'd do it from your problem because this is basically your problem that we're doing right here. Does that make sense, Dan? So these are the numbers that you posted about the children having vitamin D deficiency. So basically, I just changed the context of the problem from vitamin D deficiency to we sampled 2,400 students instead of children, and then we have 24% of them think we'll lose to Alabama. 98, yeah. 97 is a weird one. I don't know that off the top of my head. I know 98 off the top of my head. So let's identify the notation right here. Who knows any of the notation? I will say this condition 1 is random. We randomly selected these students. Condition 2 is 10%, which means this needs to be less than 10%. And condition 3 is success failure, which means we need at least 10 successes and at least 10 failures. So we would check here. Let's write down the conditions while people are on notation. Random. It says it is random. 10%. Less than 10% of UT was sampled. That's good. And then condition 3 is NP needs to be greater than or equal to 10. And NQ needs to be greater than or equal to 10. And we're going to need some notation for this. Who can help out with some notation on this? What do we have here? We need N, we need P, we need Q. And I made a simple mistake right here. We're doing confidence rolls, and we need NP hat. We need NQ hat. So where do we have any of the notation on here? Where's any of the notation? We probably meet all our conditions. We do. Where's any of the notation on here? Any bit of notation. Even the smallest bit of notation. So P hat is the sample proportion. Q hat is the complement of the sample proportion. P hat, nice job right there, Charlie. 1,000 points. 1,000 points if you're watching. I appreciate everybody. Good practice. This is P hat. So in Q hat, and Charlie's rightly doing it, Q hat is just 1 minus P hat. Once you memorize that, and then what are we going to use the confidence roll for? And once you memorize how to get Q hat from this, so Q hat is going to be equal to 1 minus P hat, so 0.76. So Q hat is 1 minus P hat. They have to equal up to 1. So we can put right here, this plus this equals 1. So they have to add up to 1. P hat plus Q hat equal to 1. And hey, what's up, Soccer Rob? So good to see you here. If you have a question, let me know. Test coming up. We've got another 2-on question right after this, but let me know any question. When I used to wait tables, I put things in my queue. I would just have my brain running. David M. Lane, don't be broken. Did the internet break? Ooh, what if David M. Lane's side David, oh, it said it can't be reached and that just works. It's trolling me. The internet's trolling me. Okay. So here we are. Here's how you find out the percentages that you need. You'll put in here 98%, and I want everyone to see what we get. We have shaded the middle 98% of the curve. So we have the middle 98% of the curve shaded, and this is a 98% confidence interval. You click this button here, you go to between, and then you put in the percentages you want. You can put in a 95, a 99, whatever you want, and this is what you use the confidence level for. And please note, if you go from something like a 90 to a 95 to a 98 to a 99, you can see it getting wider and wider and wider. This is what I mentioned at the end of the video last night. So the z-score is 2.3263. So let's go here and mark this as our z-score. So that's our z-score of 2.3263. From here, we're just going to solve using the equation. So we have all of our notation marked, and we can check our condition right here. So meant to ask you last time, but isn't RMSE typical error the model makes? Same thing? Yep, they are. You got it. Nice job, Soccer Rub. The RMSE, so let me put this in the chat. RMSE equals to RSE equals to typical miss. So that is it. They are all the same. The residual standard error, the root mean square error, and the typical miss the model make are all synonymous. Great job right there, Sakura. Excellent question. And let's solve this by going here and going to 0.24. That's how many people we expect to say, or how many people did say in our sample. Yep, you got it, Sakura. You're 100% right. You're welcome. Great question. Good to confirm these things. And that's how many people think we will win against Alabama. So we pass every one of these conditions. We are green. We are good to go on all 3 conditions. 3 conditions are good. Now we just solve the equation of p hat plus or minus the z-score, p hat, q hat over n square root. And so when we think about this, we have here that the last part of the interval is going to be the margin of error. So this right here is the margin of error of the interval, and this right here is the center of the interval. So we have really 2 parts. We have here the center of the interval, and then we have plus or minus the margin of error. So let's solve for the margin of error by plugging in the numbers. We're going to take and plug in the z-score of 2.3263. Square root, and then we go 0.24 over, and then good. And then we go plus or minus. And there it is. There's the mathematics. And so now we just take and we multiply. And there's that. That's the margin of error. So it's about 2%. So this right here, don't round it till the end. But what is the interval? If that's 2%, what's the interval basically going to be? So, of course, carry all your decimals till the end. Make sure you don't round. I just type everything into the calculator. But that's about 2%. And since I'm solving a theoretical problem where I can just kind of write down the answer, it's 24 plus or minus about 2%. And so my interval is going to go from what to what? My interval will go from blank to blank. So since it's 24 plus or minus 2%, what will my interval go from? 24 plus or minus 2%. What will be the lower bound of the interval and what will be the upper bound of the interval? It'll go all the way down to 22%, and it'll go all the way up to 26%. So that is the lower bound and the upper bound of the 98% confidence interval. Why is it a 98%? The problem said it, and we got the z-score. Yeah, that works. Because you'd say it's inclusive. Yeah, that works. Oh, so I should put that right here. Oh, good point. Because they're inclusive. So we should put an inclusive bracket on it. And so, yeah, I would put that right there. It's because we'll interpret it more. We do more of an interpretation in this class. So when I do the interpretation, I'm going to go to my interpretation page where I already have it. Remember, here's our blank interpretation. So we're going to copy one of these. And then we're going to go right here and we're going to say, I am 98% confident that the true, we already have true, proportion of students who think we will lose to Alabama is contained in the interval, and we can do 22% if we want, to 26%. And that's kind of why we don't worry so much. Alabama, sorry. Misspell you Alabama right there. But I am 98% confident that the true proportion of students who think we will lose to Alabama is contained in the interval 22% to 26%. Oh, you're fine. Yeah, I would. Well, in the visualization 8 question, you want to interpret your interval the following way. You want to make sure you interpret it the following way. I am blank % confident that the true blank is contained in the interval blank blank. I think so, right? I think that's all it says. It should say check the conditions, but I don't think it does. I could take a quick look at it again, but I don't think it says check conditions, which I wish it did. I wish it said check those conditions. So we get practice with random 10% and nearly no success failure. Pause. Condition 3, pause. But I'm pretty sure it just says to do the 4 points of a confidence roll. Let me see. I never want to put out wrong info. So here's the visualization right here. And then we're going to do Gigi's question next. Create 92.3% confidence interval about the proportion of students who smoke marijuana. Take a screenshot of the bar chart, frequencies, and confidence interval and insert them into your Word document. So you do need, just make sure you have everything in the following screenshot. So you want to make sure you have a screenshot just like this. Make sure it's a random sample. This one's not a random sample. And then include a short write-up of interpretation of the confidence interval, making sure you include the 4 points of each confidence interval. Note the proportion of the population of interest here is 2 on students, and the parameter of interest is the proportion of stat 2 on students who have smoked marijuana. So, yeah, that should be pretty clear. That should do it. You should be pretty good. Great work, Charlie. I think you've got it. I think you should have some excellent work on that. Can I use function? Yep. Associate. Great job, Soccer over there. Yep. Associate will find Spearman and Pearson with 2 quantitative variables. Spearman and Pearson, which 201 should know that Pearson is correlation, and then 320 knows about Spearman correlation, which is ranked-based correlation. And so Spearman and Pearson are both quantitative relationships between data. And let's hop to Gigi's question right here. Mondays, or was it Tuesday? Yesterday, I think, was so busy. It was so cool. Felt like old days when I'm running around the office. Sometimes I'll do like a 3-hour thing of office hours, and everything will go so quickly. I'll go in, and there'll be people there, and just be running around. Crazy. I am getting the homework question going right here. We'll have the office again sometime. We'll all be back. I think I have the wrong one right here. It's sampling distribution. We already did this one. Here we go. Found it. Brian is blind, but what's new? Brian's always blind. So the environmental agency one. Let's find that one. The environmental agency. I need a third monitor. You're welcome, Dan. Have a great day. I hope you got 100 there, man. Environmental agency. Environmental agency. Where are you at? Vitamin D. That's what we just did. It is believed. Editors. Environmental agency. Okay. So here we go. An environmental agency worries that many cars may be violating clean air emission standards. Actually, wait, we should have one. I need to talk to my department about that. We should have it. I don't know why it's not here. That was a while ago. The agency hopes to check a sample of vehicles in order to estimate the percentage with a margin of error of 4% and a confidence of 90%. To gauge the size of the problem, the agency first picks 60 cars and finds 15% with faulty emissions, or 15, excuse me. How many should be sampled for a full investigation? Okay. Lots of notation in this problem. So much notation. So what should we start with? We need some help with the notation right here. Okay, notation. What do we got? What do we have right here? Any sort of notation. My kingdom for some notation right here. I need help with notation. This would be a very hard test question problem. This is a lot of algebra. First step is to identify notation in this. Once we get the notation, we can start making some moves on it. We can start getting the problem worked. But I need someone to at least tell me one bit of the notation here. Any notation. We're going to have a Kahoot on Monday. It's going to be crazy. We have open class on Monday. Oh my gosh, Charlie. Great work, Charlie. The margin of error is 4%. That is correct. So that's the margin of error of the interval. The confidence level is 90%. So this is going to help us find the z-score. So that's going to be related to the z-score. The z-score is 1.6445. No, it's 449. Got to remember all those decimals. How do we get that? We go to the David M. Lane applet. Here's the David M. Lane applet in the chat again. Yep, uncertainty in the slope is standard error of the x variable. That is correct. Yep. And so the 90% confidence interval is this. And there's the z-score, 1.6449. It's just extra digits. It's 1.6449. Trust me on that. I've seen it. If you don't believe me, let's go right here. Let's find out for certain. Is Brian correct? So it'd be Q norm, and it'd be the following 1.6449. It does round up to that. So there it is right there, 1.6449. Hey, what's up, Andrew? So good to see you here. We're talking about some z-scores right now, finding out, making our confidence intervals. So good to see you, Andrew. Got all those points. Oh, Mewbot's not here. I broke the universe. I'm waking up Mewbot. We have to destroy the universe to wake up Mewbot. Mewbot, get out of the way. Trying to... Okay, Mewbot, you broke the pens. Mewbot is probably awake now. Oh no, I didn't wake up Mewbot. Sorry, everybody. Andrew reminded me, because Andrew is one of our legends of the class. Yep. There we go. Mewbot snaps. We have a Thanos snap that I should be able to do. And so I don't know where my Thanos snap is. We made that. There's P Hat right there. So P Hat, nice job, Charlie. You are among the lead right there. And Charlie, we can always make you a legend in the class. Charlie, so glad. Thank you for attending all the streams and all the practice for when we solve this problem. So this problem right here wants us to solve how many should be sampled for the full investigation to get a margin of error of 4%. So the full equation is going to be P hat plus or minus the z-score, P hat Q hat over n square root. Now, the problem is they have an original n, and they want to talk about like what full sample should they need now. So this n right here is just a preliminary kind of like n that we use to figure out an estimate of what the proportion is. So now we want to do a bigger study with a larger sample size. So you could technically call this n1, and this could be your second sample when you take the second sample. Does that make a little more sense there, Gigi? Because the first time you did this, you were just trying to estimate what p hat is by taking a preliminary study, like they're saying. And then I'm writing n2 right there to say, okay, this is from a second study. And technically, proportion would also be n2 also. Yeah. And so this one right here, well, we know the z-score, right? So what this question is we're only focusing in on the margin of error, which is this. You're only working on the margin of error. So because of that, what I'm going to do is I'm just going to remove this. I'm going to say this is the margin of error. Does that make sense right there? This is the margin of error. The margin of error is equal to z times p hat q hat over n square root. So that is the margin of error. Where does the p hat go? So the p hat will go in there. The p hat will go in there. That's our estimate of what p hat is. We don't truthfully know the new p hat, but we're going to use the estimate of 25%. And then q hat is going to be right here at 0.75, 1 minus p hat. So it was p hat x z. Now it's just z. I am confused, Charlie. This is z times p hat times q hat over n square root. And we're just calling it n2 because it's the second sample we'll be taking. So the p hat was obtained from 15 over 60. Let me write that right here. Does that make sense? Oh, no, it's a 2, but no, it's this is a 2 down here, but I'm just putting it here it's a subscript. So it's representing the second sample, and these are my z's. This is the z-score. So that is a z-score right there. The equation before was p hat x z square root. Now it's just, yeah. So let me try to explain that right here while we're doing this. So the full equation is this right here. P hat plus or minus the z-score, then times this right here. But the only thing this question is asking about is it's saying we want there to be a 4% margin of error. So since we want there to be a 4% margin of error, this portion of the equation is the margin of error. Does everyone understand that? That everything after the plus or minus is the margin of error. Does that make sense, Charlie? That is the margin of error. And so we could solve that. And if we solve it, what would that equal to? So that is the margin of error. And according to this, if we solve it, yeah, and that's why p hat good. Yeah, I think you see it now. Yeah, that's why p hat goes away, because all we're doing is saying, oh, we just want to solve this because this should be equal to 0.04, which is the margin of error. So we're going to solve this so that it equals to 0.04, which is the margin of error, 4% that we're calculating. So we're just using kind of what we know that the margin of error must be 4% according to this problem. Yeah, exactly. We don't want the full confidence interval. We're just solving so that we get a margin of error of 4%. We're not solving for the full confidence interval. Yeah, it's such a crazy problem. These problems, the first time I did them, I was like, wait, what are we doing? Okay, we got to solve it. How? Do we have an equation for that? So don't worry. The worst thing a student ever said to me was, it might have been my first or second semester teaching. Hopefully it was. It was last year. They said to me, they looked at me when I was having problems with a problem because you make mistakes, and they looked at me. They go, "Do you even know how to solve this?" And I was like, "Oh my god, I felt so bad." I did know how to solve it. It's just we all make mistakes. We all make mistakes. So don't worry, I've solved this problem hundreds of times. The tricky ones are the multiple choice ones where the questions are a little bit off. Those can be tricky. So right here, what we're going to do now is probably my favorite way to solve this problem is to solve for n before you do any work. So here's what I'm going to do is I'm going to work the algebra so that we solve for n. So watch the algebra right here. We're going to go ME divided by the z-score because that's going to cancel off the z-score over here. So that'll cancel off that z-score by doing that. Now we have p hat, q hat over n. What is the p-value of the test of equal spread? Are we supposed to get it through the... I can't tell you exactly how to get everything. I can kind of confirm stuff, but I can't tell you every function. So I know what you're doing, but no, don't worry. I can't tell you exactly where to get it, or I'll be telling you how to do the take home. But I can't tell you exactly where to get it. Definitely look through the no. Don't worry, Sakura. Great questions. I'll tell you everything I can tell you and can't tell you. But look through the notes and try to figure out where we do the test for equal spread and how we get it. And I bet you'll find it. So be like, this is a test, like something like a condition or something like that for the regression. You got it, Sakura. You're doing great. And you know what? You've got 2 more days to do. Like, you are doing excellent right now because I'm sure I'm going to get emails on Friday night. It's, I sometimes I think to myself, I shouldn't answer the emails at 11:55 at night. And I'm like, no, I got to do it. I don't know. Part of me is like, no. And the other part of me is like, okay. And then sometimes I just go to bed. Hey, what's up, Campbell? So good to see you here. And, those are the interesting ones when I get the late emails. Like, Ryan, everything's exploding. I'm just working the algebra right here for this problem. This is just relaxing time working algebra right here. So now we can... I didn't put the hats on them. Well, those are going to go away. Okay, so there we go. Okay, what have we done? And I stopped calling it N2 afterwards because it's just sample size. But do you see everything we've written right here and what I've done? Does this make sense here, Charlie and Gigi? With what I've done with this, how I've just worked the algebra so that now we don't have to, So I've just worked the algebra so that it's solved for n. So I followed through with the steps by bringing over the z, squaring everything, and then flipping you can flip equations. I think that's something a lot of people don't know, is that if you have ME over Z and P hat, Q hat over N, you can flip both of them. So that bottom equation is the one that you use in order to solve this. Yeah. That we did it. So now we just put in our numbers right here. I think a lot of people get stuck on the z-score also because they're like, how do you get the z-score? And the z-score is obtained via things like the David M. Lane applet. It's just the percent or the numbers on the normal curve. And so the z-score, we're doing a 90 what percent? 90 what percent? 90%, right? Because there it is there. So 1.6449. And now we go over the margin of error, which is 0.04. And we square this, and then we multiply by all that, and that'll equal to n. So which number? It's just the n right here. So this n, this one can't be solved with the TI really well. You can use the TI though for a lot of the confidential stuff. Andrew's so right, and maybe I'll show that some today. But the TI, so I show it a little bit because not everyone has the TI. So I'd hate for someone to be like, well, I don't have a TI. I guess I'm stuck. But the TI can be a huge help for these. And so it should be 30. I think it's going to round up. 318. Be careful. It rounds up. Don't forget that. I think these round up. Oh yeah, we could code this for sure. So here, watch this. You ready? Here, let's code it. We got to do this. round up to the nearest whole number, 318. So watch this, Charlie. You ready? About coding it, it's so easy. Watch this. Let's go over to R, and let's make a function called, let's call it, we'll call it something in a second. So what did we need in that equation? In that equation, we need p hat, q hat. Well, we just need p hat. So let's go here to p hat, and let's put in 0.75, and then q hat is equal to 1 minus p hat. The confidence, or the z-score, if you remember a moment ago, I had it by q norm, and I entered in 0.05. So if someone entered in 90% right here, it'd be 1 minus 90 divided by 2. And that's the z-score. So that's the z-score right there. So someone can enter in there. There's the z-score. And then we need to, what else did we need? The margin of error. Margin of error was 0.04. Okay, so I think we have everything we need right now. Now we just need to write the equation, which was p hat times q hat multiplied by, we have it, I'll show it so everyone can see it if everyone's wondering why I'm doing this. Here's the z over me squared. So z over me, and then we go to squared. And p hat's not found. I must not have stored it. Did I store p hat? There we go. And then what we want to do to this is we want to do a thing called ceiling. Ceiling will round it up no matter what it is. So floor rounds it down no matter what the number is, and ceiling rounds it up no matter what the number is. So with this, I know, right? But here's the better part. Here's the better part. Here's where we turn it into a function. We go right here, and we take all of these values, and this is what we really need. We go here and we say solve environment. So with solve environment, we're going to go fun, and we're going to store a function right here. Our function needs to take p hat, z, and me. So let's go right here and go return of this. There's our solve. And then we say read line. I'll have this solved in just a second. Read line as dot numeric. There we go. And then the read line should say, what is p hat? And that'll do that. We store this right here with p hat. And then we take our q hat right here. Oops. Didn't close that. There's q hat. Our z needs to go right here. And we say, so z goes right here. Enter confidence as decimal. There we go right there. This will store into, let's call it conf for confidence. And then this will go right here. And whatever they enter will go right there. And then the margin of error will go right here. And we'll say margin of error. And what is the margin of error as a decimal? Okay. So this should do it. I think we have everything working right now. Little 32474 work right here. What are you doing, computer? Okay. There we go. Let's see if it works. And between... Oh, yeah, we can do that one next. You got it, Gigi. And then, Gigi, do you have your... Because now the solve environmental one should work. Does anyone have their p hat? We could have it where you put in x and n, and it could solve for it. Right, that was a little more complex, and I thought I won't be able to take it. No, you're fine. This is 474. This is more 474. This is more 474 than 320. So don't worry. We don't really get into functions in 320. We do it in 474. 320, we wouldn't expect you to be able to do this. 474 is where 320 is regression. And so you could ask, Sakurab and both Andrew are here, who've taken 320, 474. Got an A- in 474. Look, Andrew, nice job right there. So, and Andrew took 201 with me, 320, 474. And he can probably tell you that we wouldn't, we don't get to these things till later on. Like, we don't ask you, so what is the confidence level? 0.90. What is the margin of error as a decimal? 0.04. And then it returns to you the number. So now this right here is a solver. Yeah, exactly. This solver right here will get you the answer. If you said, oh, my margin of error or my p hat was 0.40, my confidence is 95%, and my margin of error is 0.05, this will solve for you the answer to any of them. So this will literally solve the question. We could have made it so that it gave X and N. So we could have said, what is X, what is N, and we could have had that solved for P hat. It'd be so easy to change. Like we put right here X, and then we put right here N. So we say, what is X, what is N, and then we just do P hat equals to X over N. So now it changed so that it'll solve for us. So now it says, what is X? 15. What is N? 60. What is the confidence level? 90%. And what is the margin of error? 0.04. And it gives the answer. So, yeah. So if you look at what we've done right here, we've now made it so somebody could use this from the start and literally input their numbers, and it'll just solve the answer for you. So you're like, oh, that's my X, that's my N. But you have to know how to solve it. So this is why, it's like once you know how to solve the problem, you could create a script right here that just runs it for you. Or what if you could like scrape the problem for it? Might be a way to do that. But this is why I love coding. This is why I love just, practicing this kind of stuff, just writing a function that solves things for you. But yeah, I love read lines. One of my favorite things to use because you can like have it just ask you the question and then you can store it. It took me a while to realize you have to put the as.numeric around it to make sure it stores it as a numeric value. So the way R sees these objects. So what other questions were there? Oh, and then we have Gigi give another one. There is a part of E that states 95% of the days between, that would not be correct. Sorry, Gigi, it took me a while to respond to that because we're not talking about the days. We're talking about the true proportion of like for the population, for everything, not just on a day. Let's do that one again. It's really good practice. I think it's going to be right here. Yeah, here we go. Okay, so this one's really tough because it has very, it's going to be, it's not the parameter right there because we're not saying on a given day, we're saying for like all days. If you look right here, we have that 78 is our confidence interval for the percent of time the packages arrive on time plus or minus 9%. So we go back to our interpretation, our excellent interpretation. And here it is right here. And what was the percent on it? The percent was 78 plus or minus 9%. So it would be 69% all the way to 87%. I am 95% confident that the true proportion of all orders that arrive on time is contained in the interval 69% to 87%. So what we're going to do right here is we're going to take this awesome, perfect interpretation. It's so beautiful. Amazing interpretation. We're going to take this interpretation. We're going to kind of leave it on the screen as we do this problem. And we look over some of these bad interpretations. So we want to keep our good interpretation up here in the corner, and then we want to see the bad interpretation right there. Between 69 to 87% of all orders arrive on time. That doesn't even mention confidence at all. I don't see any sort of I am blank percent confident that the true proportion of orders that arrive on time. So this is not correct. It implies certainty, so it's not correct. 95% of all random samples of customers will show that 78% of orders arrive on time. What are we talking about? We're not talking about the random customers. We're talking about the true proportion of all orders that arrive on time. So this statement is not correct also. And when we say that 95% of the random customers will show 78%, do you think all of them will show that? None of them will show that? Probably a lot less than 95%. Yep, it's definitely C. And great job, Gigi. Excellent work. One can be 95% confident that the true proportion... Ooh, wait a minute. So wait a minute. This one's fun. What do you think about that one, Gigi? One can be, it sounds a lot like I am, confident that the true population proportion, that sounds a lot like true proportion, and we're talking about the parameter of interest, which is for our population, of orders that arrive on time within 3 days is between, yeah, that's totally correct. It's so similar to what we're writing, and you should know a little bit of like variation within it, that you can say one can be I am or we are. There's so many ways people say confidence intervals, but you need these key components. And if you notice the key highlighted components, it does say 95% confident. It does say proportion. It does say true right there of all orders that arrive on time is contained, is within. So these are the real big things you need. And so that is definitely correct. What? If I get something wrong, it might be because I clicked off screen. So that's definitely correct if we meet all the conditions. Am I blocking it? No. I need to go a little smaller. One can be, what did it say? One is 95% sure that between 69 to 87% of the orders placed by the sample arrived on time. Can anyone tell me what P hat is? This actually goes back to a previous question. Do you remember the one we were just doing a moment ago? Because when we make a confidence interval, When we make a confidence interval, the confidence interval of equation is going to be p hat plus or minus the margin of error. So it's p hat plus or minus the margin of error. So what is p hat? What is p hat in this problem? Do you see what p hat was? What did they observe in a sample? P hat is the center of the interval, and what did they see in their interval? What did they see at the very center of the interval? I think it might be right. Yeah, exactly. In the sample, we know 78% arrived on time. Bingo. So we know it's 78%. About the last question, I just checked my notes and found the function is, yep. You got it. Sakurab, you're doing great. Excellent work, Sakurab. So on 95% of the days between, no, it's not on days. It's the true proportion. It's not like on a given day, there's a 95% probability. So that's the interval is about the parameter, not the days. 100%. Yep. It's not about days. It's about the parameter. It's like for all orders, not on a given day, because there might be variation within the days. We're talking about, I am 95% confident the true proportion of like all the orders for all time is contained in the interval blank to blank. So this is a great question. I love this question It's a really good review of wording question. Yeah, great job. Hop on that Zoom call. Great job, GG. Excellent work. Thank you for swinging by. And if I miss a question, just re-ask it. And yeah, Zoom call. You got it. You know, like if you go back in time a year ago and you're like, I have to go on a Zoom call, people might be like, what's Zoom? You're like, oh, it's this thing you talk to people on. It's like Skype. You know what Skype is? We're like, oh yeah, it's like what my parents use. My parents use Skype. They talk about that a lot. You're like, yeah, it's like that, but it's like, I don't know. It's just a video conferencing call thing. And now everyone's like, Zoom. So a catalog sales company promises to deliver orders within 3 days follow-up calls. So it wants the proper interpretation right here. I am 95% confident the true orders arrived on time. It's contained in the interval blank to blank. And I think that's it. So there we go. We got that one out of the way. Here we go with a make a confidence interval 1. So this is making a confidence interval. Whenever we're making a confidence interval, we need to know the right formula and the right notation. So let's make this really big right here. If you have questions, let me know. I'm just kind of working through some problems. That's what I do. I work through problems. And let's take a look. A philanthropic organization sent free mailing labels and greeting cards to his random sample of 100,000. Oh, what problem did I say? Was I going to do it via code? I love doing things via code. Because I can code this one too. I could code this problem in 2 minutes. Let's do this problem a different way really quick. I can code this problem in 2 minutes. Get this problem code. I probably code in less than 2 minutes. So here we go. We'll put this timer on the clock right here. So this is when you're given X and N, make a confidence interval. Okay. Might be able to code in less than 2 minutes. Okay, so what we have right here, I've already got this written. So this will help me solve the z-score. So we'll ask somebody, we're not going to do it as a function. So this right here is going to be the z-score. And then we need the x. We need p hat, which is x over n. So we need to put in what x and n are. So we'll put in that x is equal to this, and n is equal to this. And then that'll give us p hat. And then we do p hat and plus the z-score times, and let's do that. And then we'll do minus p hat. Oh, we got ourselves q hat. Q hat equals 1 minus p hat. And I thought I could do it in 1 minute. And then, so p hat times q hat over n. And then we square root this. SQRT. And then we go minus. We'll do the minus first. Okay. And that should do it. What is x and n? 4752. So 4752. Oh, unexpected symbol. What? P hat times q hat. What is? Does this not solve? That solves. Oh my gosh. There we go. There we go. There's the answers. And if we want to round this, how many decimals does it want us to round to? Let's round it to 4 decimals. And there's the answers. So we did in just under 2 minutes. 0.04. Oh, but we have the bigger number. Wait a minute. Did I do the... Oh, I did the negative z-score. That's why. I'll just switch the positions. So 0.0458 to 0.0493. So 4.58, 4.93. 4.58, 4.93. So 4.58, 4.93. And we check, is 4.7 plausible? Yes, it's in the interval. And there we go right there with that. So the whole point of test 1 is to understand how to do it by hand. So, well, so the whole point, especially with this right here. So great question, Charlie. Like, what's the point of this? The point of this right here would be to know what statistical technique to use. And there's an even easier way to do this that uses slightly different techniques. I don't know if it's going to get the same answer. It uses a different type of test, which is just the one prop test right here, or prop test. So I could put in 4752, and it gives these intervals right here. If we compare my interval to that interval, it's slightly different because it uses a slightly different test. It does a chi-squared test on it. Very careful, because we're talking multiple different types of tests. Something Chelsea is doing, especially with her boards test, is they ask you, like, what technique would you use to examine this data? And they want to make sure, yeah, they are real. Yeah, they're really close. It's just a slightly, it's like someone who uses a Phillips head versus a flat head. It's like they're both screwdrivers, but they do slightly different things. So, and you look at how much quicker that is, because I just need to enter in, prop test and do this. Now, I could turn mine into a function also, where you input these values like I did previously and call it like 1 proportion z test or something like that. Exactly, yeah. And so it could make some differences. There can be some differences. It's a non-symmetric interval. So you might say, well, what's the point if I'm just going to code this? The point is kind of to know, the biggest thing to know from this class would be when you're presented with this type of problem right here. When you're presented with a problem right here that says, we're trying to make a 95% confidence interval, to understand what a confidence interval is doing. A 95% confidence interval is trying to estimate the true proportion of people who will do something. So we're saying, what is the true proportion of people who are actually donating to this campaign? We observe in a sample 4,752 people donate, which is a sample proportion of 4.752. So instantaneously, you should know the notation right here. If we take this problem and we go and we do X right here, I might have been able to solve it quicker by hand. Truthfully, I think I could have solved it quicker by hand. And so we have X, we have N, and then immediately here, oh my gosh, X over N equals P hat. And so this is going to equal to 4752 over 100,000. And this equals to 0.04752. Thank you, Ben. I do it for practice too, because I want to make sure I can still, the quicker I can do it, the more, the more practice you get. And so all potential donors, sample frame. So for this question, this is like some big philanthropic organization. Imagine like the Red Cross. Imagine the Red Cross sends out something to 100 random customers, not customers, but like, Red Cross. You guys know Red Cross? They're out at Christmas. They're like, bing, 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 bing. They're ringing the bell, and they want to know if people will donate to the Red Cross. And they send out something for Christmas, and they say, even $1 will help save blah 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 blah. So imagine the Red Cross sends something out to 100,000 people. So the Red Cross might have access to, let's say, 50 million people. So the Red Cross, the population of donors the Red Cross has is 50 million from their lists. Over the years, they've gathered huge lists because you can get lists of data from tons and tons of places. So they have a list of 50 million people, and they say, well, what if we were to send out donation things to everybody? And now this is like a donation packet that costs them, let's say, 80 cents to send. So does that make sense? I was literally hearing figures about stuff like this today about grassroots support and the cost it takes to get, someone to donate, because, sometimes it costs money to get people to donate. So you're like, wait a minute, you're trying to get money, you're trying to get donations, and it costs money to get donations. That's just the business of business. Pretty crazy. So if the Red Cross has access to 50 million people, that would be their population. And so maybe some of these people have, they don't have the right mailing address for, so they wouldn't be in their sample frame. So, but they still want to understand anybody. So you could maybe say, let's write it down this way, because I think Charlie brings up some really good points. Population, anyone the Red Cross could get a donation from. This is all people who could possibly donate to the Red Cross. Sample frame, all people Red Cross has mailing address for. Sample, the 100,000 people the Red Cross sends out to. So does this make sense right here, Charlie, that the Red Cross, their population of interest is anyone who could possibly give them a donation? Their sample frame would be all people Red Cross has a mailing address for, because they're going to send out things to people, and they could theoretically send to anybody they have a mailing address for, because they're going to say, okay, well, we have the mailing address of 50 million people, so that's their sample frame now. Does that make sense? So the sample frame would be probably the population is bigger than the sample frame, because I think it's where I maybe made it a little confusing, because there might be people in the future that they could possibly get. So the population is pretty much anyone's money that they could get from. Exactly. So because that's who they're interested in. Anyone they could theoretically get a donation from is their population of interest. They just want, but they have only access to people with mailing addresses. Exactly. The sample frame are the people they have access to. So they want to, see, will people donate to us if we mail to them? And so the people they have access to are their sample frame, which might be 50 million people if they have 50 million mailing addresses. I chose 50 million because, because the population is even bigger for CUS. They sample 100,000 people, and that's got it. So, and from here, the problem kind of solves itself, because we know what P hat is. Q hat is going to be 1 minus P hat. Why am I rating P hat that way? So Q hat's going to be 1 minus P hat. And oh my gosh. 95248. This problem right here is so easy to make a mistake on because of all the decimals. So with this problem, when you get down to the final solve on it, it's very easy to make a mistake as you write it out, as I am just doing endlessly. Z-score, square root, P hat. And we put a star there. So, or if your handwriting is really bad like mine. There's so many restaurants I want to try here in College Station. I want to go to them with Chelsea. Oh, we need the 99% confidence roll. This is 2.5758. How do we know that? David M. Lane. Let's go check it out on David M. Lane. David M. Lane, I'm going to put in the chat if anyone's watching and needs it. There's the David M. Lane, and we go to 99, and there's the confidence roll for it. And this meets all the requirements. We assume there are more than 1 million people donors. Yep. Oh yeah, and we have. Oh yeah, because how many successes were there in the sample? So how many successes were there in the sample, Charlie? Good questions right here. Good practice. How many successes were there in the sample? How many successes were there in the sample? For the visualization stage, when you find the z-score, we won't actually need to do that. Hopefully I didn't cause confusion with that. So Nicole, great question. You won't actually need to find the z-score. I was kind of just adding on some notes to the end of the video. And you don't have to solve it by hand. You just have to solve it using a jump. And so I'm kind of just adding on some notes. I should add like a note in the video. Like you don't actually have to solve the rest, because I know a few people have asked about that already. But I was just adding on some notes right there. Does that make sense, Nicole? I might even send an announcement saying the z-scores are just me showing z-scores and showing how they work, because that's one of the biggest questions I get is how do you get this z-score right here? Yeah, great question, Nicole. Thank you for hopping in and asking. It's the best thing if you check out the video, because I always want people to, when I do the videos, I don't want people to just kind of click through. Don't worry, I don't think anyone's doing that here. But I don't want people to just like skim through and be like, okay, there. Okay, that's the answer. I want people to like use it to review the concepts. So a big question I always have is, how do you get the z-score? And the z-score, maybe I should have shown the David M. Lane, but the z-score is obtained by using a site like the David M. Lane. And I want to show the concept as you get a higher confidence, the interval gets less precise. So really great stuff right there, Nicole. And so you only need the interpretation. Maybe I should have like stated that like 10 times. You only need no, because don't worry, the second or third person asked today about that. And so I just fear sometimes someone like there might be confusion. There we go. That's got the thing. So once you solve this, you will get the interval. I'm not sure if you can answer this, but just wondering, when I did the fine transformations, R gave me log 10 with the highest R squared, thus best fitting. There is a note. They're saying if the log transformation is suggested enter 0, does this mean I put 0? Yep. Mm-hmm. Great job. That is a perfectly great question to ask. Yeah, definitely, Sakura right there. If it gives you log 10 as the best transformation, do enter in 0. And that's what I'll look for when I grade it. Great job. That is exactly what you should ask. Don't worry. Didn't be scary with the other one. Being like, I can't answer that. So that's, if you solve the equation down below, it's just algebra right now, you will get the answer. So if you solve that equation down below, you will get that answer. And 4.7 is plausible because it's in the interval. We think, I'm 99% confident the true proportion of people will respond to this mailing list is contained in the interval 4.58 to 4.93. Next one. So in this one, we need to identify notation. Oh, this is one we did earlier. So we will skip it for now because we already did that one. This one right here is a sample size one. So we have a very similar thing to this from before. So here's what we're going to do is we're going to do a quick solve on it. We can come back to any of these, but we've already talked about and did the algebra for a problem just like this. So since we have an algebraic formula, we're going to take everything right here, just all this stuff right here, and we're going to replace the question. And once we replace the question, we're just going to use what we've written. So we already know that we're solving for the margin of error right here. And the margin of error is z-score, which is z star because we get to pick it, times p hat q hat over n square root. And p hat is the sample proportion, q hat is the true proportion, p hat is the sample proportion, q hat is the complement of the sample proportion, and which means it's 1 minus it, and n is the sample size. So it is believed that 23% of adults, so that sounds a lot like what they're going to use for p hat to assume, over 50, that's just a number, never graduated from high school. We wish to see if this percentage is the same for 25 through 30-year-olds. What sample size would what would allow you to increase our confidence level to 95% while reducing the margin of error to 2%? So this is going to give us the z-score right here. So we have to take this 95% confidence right here. This is a classic one. If you know z-scores, then you'll know 1.96 right here. We're going to go to David M. Lane, enter in 95, and get 1.96. That's the 95% confidence z-score. And I've dropped the link in the chat right there, so if you'll need it, that's 1.96. And then we want a margin of error of 2%. So that's 0.02. And from here, we've already written the algebra out. We're just trying to solve that this right here. Let's write it as we did before. This is the margin of error. So we're just trying to get that the margin of error is that value and then solve for the sample size. We don't have what q hat is, so let's go ahead and solve for q hat. Q hat equals 1 minus p hat. So q hat is going to be equal to 0.77 because it's just 1 minus p hat. So p hat right there and q hat equal up to 1. Good practice to know that. They just equal up to 1. P hat is the sample proportion. Q hat is the complement of the sample proportion. And now we just go down to the end. We go down to our numbers. So I think it was a 2%. Probably says round up. So it was 23 right here for p hat. Q hat is 77. The z-score was 1.96. And the margin of error is 0.02. And then we're going to round up. So let's solve it out right here. 0.23 times 0.77. Don't do it that way. 1.96 divided by 0.02. Squared it. Where do we square it? Multiply it twice. There we go. Times 0.77 times 0.23. And did we do it correct? Would it? Yeah, it would be about that much, right? Because 0.02 is a very small margin of error. I'm going to double check the math. 1701. And that's rounding it up, which it would round up anyways. 1701. Let's double check the math. Always good to double check your math. Let's see. 1.96 divided by, there we go, multiply by 2. And it looks like it's going to be that again. There we go. 1701. Does it like it? Does he like it? Does Mikey like it? He does. That's awesome. Those old school commercials. And here we go to the next one. Very similar. Editors reporting on the economy are trying to estimate the percentage of businesses that plan to hire additional employees in the next 60 days. They want a certain thanks, Andrew. Thanks, Charlie. Willing to accept a margin of error of 3% with a 95% confidence. So if you notice right here, they've got this sort of this one's tricky. I'll tell you why this one's tricky. What did this one not give us? What did this one not give us? That makes this one way more harder. But it's just they assume this one's tricky. Glad we're doing this one because I could see how someone could be like, I don't have enough information to solve this. What are we going to be stuck on this one? What are we going to be stuck on? So I'll write down the notation we have and think about what notation we don't have. This is the hardest one on there probably. 95, so z-score, that's 1.96. Now we have no more notation. What are we missing? That's a big thing right here. And the 95 is obtained once again from this right here, and there's the 95% confidence interval. And so what are we missing? We're going to solve for n. So the goal of this will be to solve for n. So the goal is to solve for n. So we should be missing that right now. The goal is to solve for that little n. And but we have right here, we have this, we have this. Yeah, we don't have p hat. So what should you assume for p hat if you don't have anything for p hat? What would be probably the safest assumption? What would be the safest assumption? Yeah. 50-50. It's the safest assumption. It'll make the sample size as large as needed. So the safest assumption is 50-50. Since it doesn't give any info, we just have to go, as large as possible, or because that'll make Q hat and P hat as large as they can get. So if you don't have any information, it's safe to say that, not safe, but the best assumption would be a 50-50 split, because it's like, well, I don't know why it'd be more than 50 or less than 50, so let's just go half and half. It puts them both equal because you have no evidence that there'd be a difference between the two. So that is the safest assumption right here. I was trying to get that erased. And so I was like, is that my screen? And so let's solve this out right here. We're just going to go down to the bottom. And what was it was a 3%, right? So I think it was 3%. 3%? Oh my gosh. I hate it when it does that. There we go. And that's not the answer, so let's fix that. I had the eraser selected. Okay. Let's take a look at the answer. So 1.96. There we go. And if it says round up, 1068. 1068. If we round up. 1068. Did we get it? Did we? Round up. And to cancel. Got it. Hey, what's up, Ashley? So good to see you here. Let me know if you have a question. We've been working through chapter 13, doing a bunch of these. Let me know. We can do any sort of question you have. Whatever you're wondering about, let us know. We've got another confidence interval one, a more traditional one right here. The number of adults that should be tested. Why are they having us solve for n all the time? These are the least fun ones. We've done so many of these solve for n's. Yeah. Let me know which one you're working on. We can work it. Basically trying to do as many of these as we can to help put them in the video. I know I'm so proud when I see like 300 people have watched the video. And obviously, I don't put ads on these videos. I put ads on the visualization videos, but I don't put ads on, because these are pure lecture videos right here. The visualizations take more time with the editing and everything for them. I'm like, no. And then we get to use the money on Kahoots. So we get the bonus for that. A doctor's note that 22% of her patients, so this is going to be the p hat right here. I'm just quick solving this one. 90% confidence, that's going to be the z-score, which is equal to 1.6449. And then the 5% is going to be the margin of error. So that's going to be the margin of error. What's up, Colin? So good to see you here. So p hat is equal to 0.22, and q hat is equal to 1 minus p hat, and that is equal to 0.78. Speedrun exam 2. I probably could. I've helped write a bunch of the questions on there. So if I had to speedrun exam 2, and I'm hoping see what I can get knocked out this weekend. I've been trying to do a little less work. I was looking at my video folder and I was like, I was really putting out like a video every 2 or 3 days. Because I don't know, I was staying up way too late. So I've been trying to be more sensible, drink a lot more water. Tons of water, like 4 glasses of water a day, which has really helped. You know, like, no, I like putting out videos. They're a lot of fun to me. Like the Smash Bros thing, oh, I was so excited. The epic speed runs, I was showing Chelsea that. She came home from work, and I was like, check this out. And I was like, watch this. And she was like, that is so cool. When I make Chelsea think something's cool, that's my like big moment right there. That's what I really like. She and I watch a lot of epic rap battles of history, and so that one was kind of for her. So to be like, you know, check this out. Yeah, Rick and Morty intro grid and Smash intro. Oh, cool. Oh, you saw with the recent one, right? I updated that one this semester to do the glow, because I finally figured out how to do stuff like that. So I was able to make those kinds of updates, which I've always kind of wanted to do, because I was like, how do I make an electricity effect around it? It's not as cool as when it goes across it, which I could maybe... There's so many different things I have to learn. But once you know how to do it and you know the buttons to click, it's all just clicking buttons. And then, you know, there's so many interesting things you can do. But I'm glad you like... It's Nick Brown, who's a former honors student who did the voice of Rick. And even Chelsea was like, that is an amazing Rick impression. It's like, Morty. I can't do it. He's so perfect at it. And Lizzie right here. They're going to come after us. I'd love it if Justin Roiland was like, if he did an impression for us, that'd be awesome. Just be like, hey, Justin Roiland, if you want to do a 2-second, you know, like, hey, Stat 201, maybe he's on Cameo. So the answer is 186. It's just like coding. Once you get it, it's just a few buttons. Yeah, exactly. That's why, you know, I've been learning more video editing. And so it's, once you get it and know how to do it, it's not that hard, but it takes a while. Take home midterm is doing me a big stress. No. I'm glad you started early, Colin. Oh my gosh. This is where I'm like falling asleep. It's so nice that Friday is more of a relaxed day. Oh, we did this one already. We already did this one. We got the solver for this one, right? Did I close out and reopen, or is it in here twice? We've already done that one. I finished it, but I'm going to take a look. Yes, exactly. Tea time? I should make some tea. Let's do the teenagers at the wheel of the accident ones right here. That's a happy topic. Let's talk about something happy. People being at the wheel of accidents. I went and voted this morning, early voting. So go and vote if you want. You don't have to. No one has to vote. But I always encourage people to vote because it's the way to have your voice heard in our democracy, is to go and vote. But if you say I don't want to, then you have the, hey, thank you, Ashley, for voting also. Went home and voted last week, and great job, everybody. But it is always a choice to not vote. I don't choose that choice, but everyone has their own choice on to vote or not vote. And I respect people who say I don't want to vote, and I say, okay. So that is the goals right here. But I truthfully think everyone should vote. I don't know. It just is a bummer. Sometimes you're like, I don't like the choices, and that's all right. And then just say, oh. So an insurance company. One thing I will say about voting. So isn't it no census is how they do congressional seats, right? So got to use your voice exactly. That's why I say two. So and we can all raise our voices and agree and disagree, and we do it all, and we all come together as Americans. So it's to me, it's all about country first, party second. I don't even really have a party. I don't care what party someone's in. It's all about we need to work together on our problems. See, like we're working together on these problems right here. We got to work together on problems. See, if we think of America as a business does not work when everyone fights against each other and you're like, this group hates the business, this group hates the business, this group wants to destroy it just doesn't work. You can't have half the company hate the other half of the company and have a very successful company. You need to work together as a company and be like, okay, we have the people who think this is our best product, and we have the people who think this is the best product. We understand they have differences of opinions, and maybe we can sway them to believe our product is better than their product. So yeah, I just people in my family vote different ways. Obviously, I have opinions on issues, which it doesn't matter what my opinions on issues are, at least in this setting. But I do think when you talk about business, because we talk about business and stuff, as a company, you have a business that works together on problems and tries to find mutual understandings and solutions together. And then, if somebody just is disrupting the company, you say, hey, you can't be doing that. You can't be disrupting our company. We got business to do here. So here we go. We have an insurance company checks police records on 594 accidents selected at random, and notes that teenagers were at the wheel of 84 of them. So N right here is sample size. We have right here 84 is X. And then this is going to be the Z-score. Once again, whenever you're thinking about what percent confidence interval it is the Z-score. This is the classic one, 1.96. So what did we first learn for a 95% confidence interval? Does anyone remember what we first learned for a 95% confidence interval? What was the first number we learned? We didn't say 1.96. We used to think that a 95% confidence interval was what? We used to think that a 95% confidence interval was what? We used to think that a 95% confidence interval would be what for a Z-score? It is 95, 1.9... 599, isn't it? If you go out more decimals. I used to think it was 2 plus or minus 2 Z-scores. That's basically what it is. So yeah, Campbell, I always hear Campbell, you're 201, right? I think you're 201 because I'm gonna say, and then you're like, no, I'm 3. No, I knew it. I knew you were 320, and I said 201. In 320, a lot of times we do it by using 2 and 320. But if we want to figure out exactly what it is, the exact Z-score of it, we can go here and do this. And it's 1.9599. And then it rounds up to 1.96. It's just a very famous classic Z-score in statistics that all statisticians are like, what's the Z-score for 95% confidence? Like 1.96. It's just very commonly known. No one's going to say 1.9599 unless they're Brian Stevens and they're acting weird. And then you can remember it's the 6 after that. So 1.96. You could say 96, but you'd be closer to just say 1.96. It's so basically 1.96. And so these Z-scores can be obtained a lot of different ways. Really, the way that we don't obtain Z-scores right now is we don't use a Z-table. It's just kind of pointless to open up a book with a table. And if you're online, it's way quicker to be like, oh, what's a 98% confidence interval? What's a 90% confidence interval? What's a 83% confidence interval or 84? You can find any percent confidence interval like this. Additionally, with software, especially with things like Jump, you're not going to actually have to find them by hand anymore. You could just go here and ask for whatever percent confidence you want by saying, let's make there's a 95, but let's make a, like your assignment, that, and there's the 92.3% confidence interval. You don't even have to find out the Z-score for this. It just solves it for you and then gives you the upper and the lower for the confidence interval. So if we're doing it by hand, though, we have to know the Z-score because the formula says P hat plus or minus the Z-score. So speaking of insurance, I just got off the phone and, oh no. Oh, I'm so glad they accepted full fault. And it sounds like you're doing all right, Colin. So you're doing all right? Girlfriend doing all right? I don't know if she was in the car or anything. Or how I'm so glad you're doing okay, man. And I'm so glad they accepted full fault. I got in 2 accidents recently. Well, it's 2. Someone hit my car in the parking lot. That was fun. It was like my second or third week in Texas. And yeah, Colin, if you want to share, feel free to. I hope you're doing all right. That sucks. I got hit in front of the standard. Some students remember that. They're like, dude, I remember that. I remember seeing your car and be like, that's Brian Stevens. The craziest part of it was some students walked by and started staring at my car, like looking at it and looking at me and looking at the car. I was like, "Hey, anything out?" They're like, no, just checking it out. And I just almost got killed. I was like, okay. It's the one time I about wanted to be like, ah, because I mean, you're in an accident and then, yeah. All good. Thanks no problem. It was just damaged bumper and taillight. That's good. That's good. Yeah. Colin, that was 2 years ago. So do we just use confident for 95% confidence slope model? Seems too simple. Maybe. I can't confirm Sakura, but definitely check out. Be like, is that the confidence level for the slope? Is this 1/7? That's not 1/7. It's very interesting repeating decimal right there. That is so, yeah, it's so awkward when people, it was on a Thursday night, I think. And so people were out, partying and drinking, apparently. And so they they had maybe a drink or two and I don't know if they drank, but I mean, it seemed like it. And then they're walking by my car, just being like, and like looking at me. And I think a few of them just stopped in front of the car and they're just like examining it. And I'm talking to the medics while this is going. Like I'm talking to the medics and they're looking at my hands because my hands were bruised up and I had burns like from the airbag. And so definitely not, I wasn't in the best of moods, we could say. I was still nice. Didn't yell at anybody. It was good that the guy in our accident too gave complete fault. He said I was looking at my phone, and when I looked up, the light was red, and they sped up. So he's looking at his phone, and when he looked up, the light was red. That's not good. And he said that. And that gave him full fault for the accident, and I appreciate that. That was very honest of him. To not say, oh, I think the light was green, because the last thing Chelsea said to me, that's a scary thing to say. Chelsea said to me, she was like, oh, the light's green. And that's, I remember her saying that because we were kind of joking and laughing, and I'd seen it turn green, and then she said it, and then we got hit by a car. So especially when I'm recounting the story, I'm like, well, she even confirmed the light was green, so I know the light was green. There's no question in my mind, which it's so interesting. If you look at interrogation videos, you should watch some of those and see how people act. And I wish I could listen to my call, because I've seen some of those now, on how people act if they're caught in a lie. And I was so forceful with the person who called about the insurance. Yeah, automated driving will be pretty interesting. Hopefully it's 100% safe, because there's been issues with planes as of late. I'm not saying, oh, it's just we have to make sure when we do something, because they had issues with the planes where the planes were, if you heard about the Boeing stuff, where the Boeing planes were bringing the nose down and they were trying to pull it back up, and the plane was fighting them, and the reason we've had some of those accidents. And so that made the news, and that's why they took down some of the Boeings, or like took them out of commission to do. Yeah, exactly. We can never be 100% confident. I'll call Jessica. That's my brother's wife. So yeah, we have to be very. It's really tough. And here's the thing, though. With all that said, what if, even if these automated cars cause accidents, which they could, I mean, all things can, because I could talk more about neural nets and how they work if you'll want to hear about that for a moment. Because neural nets are really bad if you take them out of their comfort zone. If you take a neural net out of what it understands, a neural net is going to have a major problem with that. Neural nets only work for what they've been trained on, which gets into 474 training data. A neural net, I'll show what some of that is. We'll talk about that for a second here. We can take a break from doing this. Because we've done a lot of these today. Even my mind's like, we've done so many conference rolls. 16.9. There's that. What does this mean? I am 95% confident the true proportion of teenagers who will get in an accident is contained in the interval blank to blank. So here we go. will produce confidence intervals that contain the true proportion. And the politician says 1 in every 5 get in an accident. Our interval contradicts this. Yeah. Oh no, feel free to ask about one. Sorry if I'm you're right, Charlie. I've done these problems a lot. I've done these problems a lot. The interval contradicts it because the figure the politician quoted is outside the interval. So the interval would contradict it. Did we get it all correct, Charlie? I thought I was going to get it wrong right there. I thought for sure I was going to get something wrong. That would be the time that I'd get something wrong. We did this one last week too. So a neural net, let me bring up a picture of kind of how neural nets work. I'll show 2 pictures. So what's really interesting about this is that we bring up a good picture of a neural net. So, it's a cool picture. I like this picture. Okay, let me copy over this picture. What a neural net is going to basically do. A neural net will take in what kind of variables? A neural net will take in what kind of variables? So just think about what a neural net will do. We'll take in what kind of variables? Thanks, Charlie. I appreciate it. It kind of scares me sometimes. I'm like, I don't know. I've done these problems a lot. It'll take in x's, exactly. So doesn't that sound like a lot like what we're doing, Campbell? And we do neural nets in 474. So then all that happens inside of here is a bunch of equations. And when I say a bunch of equations, I mean a lot of equations. So you have tons and 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 tons of equations. So you're doing transformations on the variables. You're doing all these different things to find out all these different ways that the variable's associated. And then what you have going on here is an output layer where you output different y's. You could output more than one y. And one of my favorite examples of this, and I won't be able to show it, is Mario Kart neural net. Seth Bling did a video on a Mario Kart neural net that he made. And so it's got a thing here. It doesn't even have 1 million views yet. So sad. Seth Bling's got 2 million viewers. So he shows what his neural net looks like right here. I'll be very careful lest I think if I won't get in trouble if let me try this. So let's try this. As my thing blinks. Seth Bling, do not copyright this video. If you see ads on this video now, you'll know why Seth Bling came after us. So Seth Bling uses a neural net to do Mario Kart driving. And so when you look at a track on the Mario Kart, so here's what he's got going on right here. This is what you see in Mario Kart. And you should have a better picture. Yeah, here we go. So this is what you see on the screen in Mario Kart. So this is it taking in the image right here of what's going on in a Mario Kart driving race. Does that make sense? It's turning it into pixels, and then it's taking all that pixels and it's doing an equation from it. It's taking all of these pixels right here and figuring out an equation from it. It's literally doing mathematics every frame the screen moves on making adjustments to say, okay, what's going on right here? Is this the same? Yeah, it's pretty much like a black box. You're right. It's kind of hidden away because all these equations are happening so quickly. And this is where we talk about the sigmoidal curve, because this is logistic regression. Because think about what this neural net is going to do. It's going to make a prediction on the probability of what? And it's right behind me right here. I'll have to vanish so we can see it. The neural net is just going to make a prediction on the what's you're going to do. Like, what is the goal of the screen it's reading with all the inputs? And then it's just going to make a prediction to do what? It's just going to make a prediction. I know this is so cool how he made all this, how he made a neural net to drive Mario Kart. It's just going to make a prediction to do what? It's going to, and what does this look like to you down here? What are the Y outputs? And I think it holds the gas the whole time. To turn, what directions to go. And you look at what's on screen, it is kind of turning a little bit to the left. It's probably holding down and left on the controllers. So it's making a prediction on what to do when it turns or slows down. I don't think he has slow. I think it drives at full speed the whole time. So the whole point of this is that, oh, there it is. That's what maps to these buttons. So it is, because it's old school, so it doesn't have 2 joysticks. But these are the predictions that the neural net makes, and it's making predictions by doing a bunch of equations from the pixels on the screen. It literally breaks down the pixels, and then it says, okay, now we have to run mathematics on the pixels, and then from the mathematics it runs, it makes a prediction right here. And so you think, well, why is this at all important? Why would any of this matter to us? Like, okay, wait, what does this matter? Let's type in this. Let's do neural net car. And if you look at how a neural net with a car, with what it's seeing, this might be really good right here. That's Tesla? It says Tesla on here. So it says Tesla, and they're showing on a different image right there. Oh, that's cool. Oh, this is super cool right here. Wait, why is it changing? Is this a GIF? What it takes to build a neural net. There used to be a really cool image of a neural net, but all it's doing is breaking down the images and trying to figure out where everything is at. And if you think about driving a car in a video game, it's nearly identical to what's going on. So here, let's take it as pretty good. So this is a neural net from Tesla, apparently. If you look at what's going on here, let me reappear on the screen. But if you look at these images, it has different sorts of kind of inputs it's taking in, trying to figure out what's going on. And that's the humongous iPad type thing in a Tesla. If you've ever been in one, it's pretty insane. You feel like you're in a spaceship. And so what the Tesla is doing is basically driving a Mario Kart cart. Does that make sense? Like, the same idea behind having a Mario Kart car drive effectively is the same idea behind a Tesla driving effectively. And the problem with neural nets is going to be if you present them with situations they haven't been trained on, because this needs to train on like what to do in these situations and learn, because the algorithm will optimize itself. So what the algorithm does is you put some sort of Y variable like avoiding accidents, or a Y variable like staying on the road. But you have competing Y variables. And our brains kind of do this at the same time. Our brain is like, okay, I'm not supposed to drive off the road, but if a person jumps out in the middle of the road, I swerve off the road. Like, it's better to, go up on the curve than to hit a person. But if there's a car stopped and you have the choice between swerving onto the curve where there's people and hitting the back of the car, you should rationally hit the back of the car. These are things that our mind does very quickly, where we're like, there's a person in the road, I'm going to swerve out of the road. There's a car stopped, I don't have time to stop, I'm going to have to hit this car because I can't swerve onto the curve where there's people. So, and it's very hard to make these decisions, but now you think a car needs to be trained about these complex decisions and so they probably create these situations. I'm not saying they go and put people in the road, but they somehow create and train it so that if these things were to happen, because if you don't train it on these things, oh my gosh, if a neural net takes on new data it hasn't seen, that's the worst thing of all. It'll act erratically because it doesn't know how to handle it. It's very bad at innovation. It's very bad at things outside of what it's learned. So you think most driving is very much the same, but your car could do something crazy. We've heard incidents of neural nets like driving into people, or cars driving into people's yards and stuff like that. There's just really weird things neural nets have done. So when you train something, do you feed it a bunch of random data? You train it on kind of the usual data, like you'd put it on, like test highways. So when they're putting on these test tracks or things like that, they're training it. So you'd want to train it in like a more of a controlled environment and then bring it more out into the real world. So training data should be accurate to real data, and then it would go through random variation that happens in the real world. Soccer was asked, isn't R squared multiple R squared? Yep. Great job, Soccer. I can say that one. Yep. Campbell, helping out. Campbell, nice job right there. Both of you 100 points. There would be a point where there would be so many AI driverless cars, but it won't be able to predict human behavior because it's erratic and unpredictable and out of. It might be human behavior might be out of. Humans are pretty bad at being random. We're pretty good at being normal. I mean, whatever normal is, but we're within the bounds of normality a lot of times. Could you make the neural net go through simulations? Yeah, exactly. That's what you do, is you feed it more and more data, and the more the neural net trains, you give it more data. Exactly. So think about this. If we did have a large network of autonomous cars driving and the neural nets were learning and evolving, it sounds scary to say evolving, but yep, let me post that in the chat, GG. It sounds like they're evolving, like it's some sort of scary thing, but the neural net evolves and learns over time. It doesn't become sentient. A neural net, as far as we know, has not become Skynet, as far as we know. I say scary things right there, like, as far as we know, there is no Skynet. Because the neural net is caught by the bounds of the neural nets is within the bounds of what it learns. And so if a neural net were to start learning out things outside of itself, I don't even know how it's possible because the code limits itself because we write the code on how it learns. So the neural net learns. Basically, a neural net is like supercharging your mind. So the neural net is still an extension of you. We have no way of making a neural net go beyond what we tell it to do. It's just we can tell it to do a lot. Oh yeah, it can learn from its own decisions, but that would be the decisions we tell it to make, and how we tell it to learn based on those decisions. Like you can put in parameters to tell the neural net how to learn, and you can tell it what to optimize. So the only way we could have a rogue neural net is if you said, like, if you gave the neural net the control over the passwords, like if you gave the neural net what to optimize, and then, or if you let the neural net choose what to optimize, and then you gave the neural net the passwords and it tried to like lock people out, then it would just be doing what a human would be doing by going rogue. And if you had it, oh god, this is horrible. I'm coming up with how to make Skynet. Because then if you had it try to figure out other neural nets and try to, oh god, no, oh shoot, I should not be thinking about this. I'm truthfully figuring out how to make Skynet. This is not a good idea, everybody. Don't do that. Yeah, it would just be a thing programmed by a human to do the things a really bad human would do. The neural net has no consciousness. A computer has no consciousness, or doesn't have any, will, or any. The computer doesn't have any will. It only has the objectives we put in it. So if we put objectives, you could code an objective that would not be beneficial. At least I would not see it as beneficial, subjectively. So I read an article a year or two ago, and these people made AI for Dota 2 and just let it go and play the game. After a week, it beat the best players in the world just by practice. Yeah, exactly. Because that's what neural nets will do. Is it's literally like, it's like, has anyone else watched Dragon Ball Z and seen Cell? If you watch Dragon Ball Z and seen Cell, that's what a neural net does. A neural net is going to learn from everything. So that's a neural net. Cell is basically the idea of a neural net. Yeah, exactly. And it'll optimize because it'll try to optimize. So if it were to go against somebody again, it's like when Cell goes against someone who's weak and he loses, and then he starts to learn what they're doing and adapt to it. That's what the neural net does, is it adapts to the variation, then figures out a plan for that. And then the more that's what Cell was doing. He was training. So think about this word of training. As you train on more and more data, you improve the neural net. And he would just go and train against random fighters. It's a very common concept. There's also what is it? There's a guy who fights the Justice League. What do you think about Elon Musk's Neuralink? Because that's the thing with minds. I don't know enough about Neuralink. It seems everything seems sci-fi till it's reality. When everyone's like, oh, because you could literally, I think they have the Star Trek things now where you can just put them on your chest, because that'd be so easy to make. I mean, you could make an iPhone small enough to put on your chest right here, and then you could just be like, boop, boop, and be like, answer calls, because we have the iWatch. We have the Apple Watch. So you could make it a transponder on your chest. It's, yeah. Awesome. No, it's been a lot of fun. We might end here soon. We got class here in an hour and a half, and I have a meeting here in a little bit. But this has been a lot of fun talking about neural nets and kind of what we do with statistics. And here's the thing, Campbell, if you're still here, there's actually the package. Let me show you real quick. We'll bring this back over. Where's that screen at? I don't know where the screen's at. You can actually make neural nets. Not that hard to make. Carrot methods in Carrot. So where is it? Here it is. So if you want to make a neural net, what is that? There you go. Here's neural nets. So there's the neural net right here. So you actually have access to this inside of R. So if you're wondering how would I code a neural net, the formula is going to be, you're going to do library caret, and we might be able to code a neural net really quick. Here, let's try coding one. I'm going to do this in class. We'll talk about, let's code a neural net. And we'll see how it does at predicting somebody's height. Wait, R is just used for, it's used for coding, for mathematics, all these different things right here. And I bet Campbell's going to know how to do this a little bit here. We won't use training data. Need help, Stack Overflow, ggplot2. That's interesting. Good to know it said that these days. So let's go here to neural net. We're going to make our neural net. And our neural net is going to be with the formula train. So train is a function inside of caret. And we're going to do y tilde x comma data equals. I'm sure, and people have seen that. Y tilde x comma data equals. And we need to load the reg class library. So we're going to do a quick neural net to see if it does any good. Probably it's not going to do good because we don't have enough time to train it. So here is the survey 10 data. And we're going to take and predict height. And we're going to predict height from all the variables. And I wonder what method it'll use. Oh, it's not making a neural net right now. What method is it using by default? That's interesting. We're not doing a correct predictive model right now. So hopefully no 474s are watching and be like, this is how you do a predictive model. I don't know what model it does by default. I'll let that run in the background right here. But what does train use by default? I'll have to look into that. So here's the method mxnet. Neural net. I just want to use neural net. And the number of hidden layers. We could try using just the default neural net. So for regression using package neural net with tuning parameters. Wait, use the package neural net? Oh, wait, here it is. Using package... What? Gotta use all those packages. Maybe I have those already loaded up. What is a period for x? Oh, it means all the x's. It means every single x. So this means all the x's. So that means every single x will be used. Whoa, there we go. Look at that. Boom. Neural net. So it was going through and putting the different weights of the variables, trying to figure out and running different iterations of the neural net right here. And I think we've got it. We created a file that is, there we go. That is our model. It's basically like regression, but this means all the x's. We used every single x right here. I'd love it if Jarvis instead. We should be able to do a summary of the neural net, right? Ooh, that's crazy. Let's have the neural net predict. Predict using neural net on, let's do that. 1. No. What did we do? We broke the universe. So let me see here. Neural net. Method, model, results. Ooh. Oh, here we go. RMSE. Wow, this did horrible. RMSE standard deviation. I'll have to look at what we did right here. But the typical miss the model makes, it typically misses somebody's height by what? Let's just put in weight right here. Is it going to destroy the universe with that? What is going on? Does it not like that? Oof. Oof. It's typically missing the height somebody is by 66.9 inches. I think it's because it's predicting 1 for everybody. Oh, I think I know why. Because I think it's using it as a categorical. It's using this it's using it as a categorical, and it's predicting. We're having some fun to end class. The reason it's making predictions of 1 right here, when we look at the predictions it makes, is it because it thinks it's a categorical variable. It's making predictions with the neural net right now, because it's making predictions like it's a categorical, and it's predicting the probability. So what we should do is we should predict somebody's gender right here from all the variables. Now let's see how we do. Okay, there we go. There's a neural net. That's a good neural net. Oh my gosh, so much fun. We did it. Everybody, Jarvis has been created. Will this actually... Oh, there we go. Final value, 144. After 100 iterations, predict. There we go. Look at that. We have now predicted all the genders of individuals right here using the neural net. And if you notice the formula y tilde x comma data equals comma method equals. So all we have is one additional thing with our y tilde x comma data equals. Let's look at the predict versus the actual. So let's say equals survey 10 gender. And then let's go here and find out the mean. And we predicted somebody's gender correct 94.27% of the time. So we predicted somebody's gender correct 94.27% of the time with this neural net. Does that make sense right here, Charlie, what I've done? I've made a neural net to predict. So I was able to predict. So all I saw was the predictions from my neural net are being equal to what someone's actual gender is 94.27% of the time. And we could try something harder. Gender is an easier one to predict. We're only doing categorical right now because it's only set for categorical at the moment. I think it's so if you like this chart, if you like this kind of stuff and messing with this, we can predict if someone has a significant other. Let's do that. Ooh, this will be interesting. This is a much harder one to predict. Okay. So we're predicting if somebody has a significant other right here. Oh no, did we crash YouTube? Oh, did YouTube crash? Are we still here? Are we still here? Okay, we're good. You guys scared me right there. I thought for a moment we really did crash YouTube. Okay, because we have minutes left. We're just having some fun with neural nets. Let's look at right here. Okay, if you look at this, ooh, this is interesting. Will that do it? No. If you look at this right here, if we were to randomly guess if somebody has a significant other, if you were to randomly guess if someone has a significant other, what would you guess? If you were to randomly guess if someone has a significant other, would you guess yes or no? Take a random person. And why would you, and you know what you've actually done right there? That's the naive model for a categorical is the majority level. So Campbell, what you've done right there is actually the naive if it's categorical because you're picking the most common level and you're saying I would guess no because the majority of people are no. So using wide, yeah, exactly. Because if most people don't have a significant other, you would predict somebody doesn't have a significant other, and the only thing you know is most people don't have a significant other, which is the Y variable. Oh, it crashed for a couple seconds for you. Oh no, I think that might have just been on your side, Charlie. So sorry about that, Charlie. So what we want to beat right here is we want to beat the naive, which is 55%. Do we beat it? 64%. That's pretty good. That's a decent increase from the naive model. It's really hard to predict if someone has a significant other, probably from all these random variables right here. But we could do a lot of different things. We could try a lot of different models here, and we could increase our neural net to do deep learning, which deep learning is just doing more and more equations. Are there any community pages I can download into R and just mess around with it? Yeah, or there should be. So if you have Carrot loaded up, so here's your data sets currently inside of R, and here's what Carrot has. So Carrot has these datas right here. So if you type data like this, you can look at the different data sets. And so I encourage you to take a look at a lot of these different data sets right here and to explore the idea of like trying to make a neural net, reading about them. I crashed 400. Wait, you crashed. Wilson, I'm so confused. Just three. No, this is 320 would code like 320 would. What's good is in 320 you would just make. We'll be doing this next class. Is we'll be making just a linear model, and so we could predict somebody's height. So Campbell, what does this code right here mean? Predict somebody's height doing what? Predict somebody's height doing what? What would this code read right here? Yeah, we'd still use this software. Yep. And so if you ask a lot of people, predict using all other X variables, bingo, you got it. That's predict height using all other X variables. And then we can make a summary, and the model's going to look a little bit crazy because it's going to have all the X variables. Can't find summary. There we go. So it's going to have all the X variables here. And so that's predict someone's height using all the variables. Yeah, it's not Campbell, Sakharov, what advice do you have? Does 95% confidence equal to slope? I can't say Sakharov, buddy. So Campbell's giving some good advice right there. What Sakharov, Campbell, and Wilson, did you take 320? What do you think about 320 so far? I think the coding's not the harder part of it. Yeah, I know. Great job, everybody. Yep, got our meeting at 3. I think the coding's not as bad. Once you get used to it, yeah, I'm so glad. Thank you so much, Sakura. Coding is it's great to put on your resume. It's a huge skill set. The more you practice, the better you get. And Charlie, if you want, I can send you the data camp invite. Message me, Charlie, on Discord or email. I'll send you the data camp invite. Yeah, it's a little challenging, but and there's a lot of help. We're totally here to help. It's just practice. At the start of the semester, the more practice you put in at the start, it's like starting the semester going 50, 60 miles per hour. I'll help out with it. I'll help out with and thank you so much everyone for the positivity. I love all the positivity. That's what keeps me going. If my students ever hated me, I would just be like, I'm done. Yeah, you can, what's really interesting is you can code some rather small things. Try looking up how to program something like, here we go. Let's see. Let me find something real quick. We'll take another 5 minutes here real quick. I'm gonna find something. What'd I do? I broke the world. So let me go and look up one more thing right here. So let me say coding. Let me see if someone coded this. Oh, found it. Apparently someone did they why don't they just post the code for these things? They just need to post the code for it. Wait. Okay. Does this work? It's on GitHub. I shouldn't run random code. Looks like someone's coded Snake into R, which is a very fun classic game. But there's so many things you can... Creating a Snake game with Python in under 5 minutes. This guy, Engineer Man, really great coder. This video has 2.7 million views. He did it in Python, so anything you do in Python, you can do in R. So, gotta be careful watching his video. We'll pause this video. But he's gonna code Snake into Python in 5 minutes. So he has 5 minutes. And what I should do is I should watch this video and make my own version of it. So he's trying to code the Snake game. And by the end of it, he's coded in his own Snake game right there. So I'm not Engineer Man doing, yeah, this guy right here. Great job, Ashley. Good job seeing you here. So he did it with 58 lines of code, it looks like. So 58 lines of code. I should try doing this. I should try this for practice for myself. It's going to take me longer, and I'm probably pretty much just going to copy what he did. But then as I learn to do it and understand what's going on, you might use things I'm not. He's using random. Oh, that's where the food appears. While food is equal to none, so he has a loop checking the food. If snake 0 equals food. Oh, the position. If the position is snake equals food. So I think if the snake finds the food, then food equals none. And then while food is equal to none, I think it generates a random position for food. And then I think he's making the snake longer. So yeah, I'd have to look at all the code right here. But pretty fun. Do our things carry over to other? Yeah, oh yeah. I don't code in Python. So if key equals cursor right, then it's going to move the head in that direction. So he's saying the key press. So he's going to have it register a key press. So key equals cursor right. While true, next key, he has a function right here. So this is a function he's running, and he's going to run that. I don't know what that function is. If snake position 0, 0 in, oh my gosh, that code I'm going to have to take a look at. Hopefully he explains that fully, because it's a big portion of the code. So he's creating initial vectors. Yeah, and then he's got a timeout. Really cool. Yeah, I'll try to do it. I'll try to do this. I might do this weekend. Import curses. That's how you load libraries. He's loading his libraries right here with his import. Feel free to watch some of his videos. I could then try to do his challenges right here. Of course, I'd just kind of be replicating it, but maybe I'll try to start learning how to code like he codes. But little things like this, knowing how to do them, just gets your brain better at solving other problems. It's kind of like solving Sudokus or something. Just the more you solve, the better you get. The more things you can solve, and then you just have more tools in your toolbox. So it's kind of been a neat little thing about coding and just trying to understand the different things we're doing. Will there be a Stat 201 review today, or was that done? We're gonna finish. So the last little bit. Don't flag our video, Engineer Man. We're just chilling here, promoting you, Engineer Man. We didn't watch your video, so we're not trying to get views off of it. We're just promoting Engineer Man. Yes. Thank you, Sakurab and everything. Yeah, we're all here to help. So we'll do today we're gonna finish chapter confidence intervals, and then Monday we're gonna have a big review. Monday we're gonna review. So I sent out the links for that. I think Monday we're gonna review for class, and we're gonna have an open review, so people might be joining us. And then Monday night, we're going to do a huge Kahoot. So we'll probably do a smaller Kahoot on Friday, but Monday night, we'll do a huge Kahoot. I think we'll do the usual, maybe we'll do 40, 20, 10. So we'll do $40 first prize, $20 second prize, and $10 to do 40, 20, 10, first, second, third. So be there, huge Kahoot, big prizes, and so glad everyone. I get excited about coding. I love watching coding videos. I'll just watch someone code. I'll watch them code in another language. The better you get at coding in one language, it helps you with other languages. That's got it. Great job, everybody. Any last questions before we go? So hopefully, like we were saying, there's lots of help. So if you're wondering about any other classes I teach, we're here to help. And I'll email, we'll talk. And if I'm there in person, we do a lot of help. I miss being in person and just having people come by and be like, Brian, how do I fix this? I'll be like, let's fix this. See you in class. Awesome job, Charlie. Great job on the assignments. I will let everybody go. It is time. So, hey, Brian, I'm super late, but hey, Kiana, great job. An amazing win last night. Kiana, you were the winner, right? Excellent job. Great win last night. We just had a big fun talk on neural nets, and we actually made a neural net inside of R. So if you're wondering, here is the neural net we made. Oh, wait, what is it asking? I clicked the wrong button. Here is our neural net. So we just made a neural net inside of R. Feel free to check that out. I'll let everyone go while this neural net is going crazy. Bye, everybody. Bye.